Welcome to Land Eco Lightning Talks and Thinking Like a Landscape with Dr. Kevin McGarrigle. In this second part of this three-part series on the landscape concept, I'll briefly discuss the challenges of scale when dealing with landscapes. And this will be followed in part three by a brief discussion of the importance of landscape dynamics, or the variability in time and space. Okay, let's get started. The first important point is that ecological similarity decreases with increasing distance in both space and time. This is one of the fundamental laws of ecology and one of the principal axioms of landscape ecology, that ecological similarity decays with distance in both space and time. And this is illustrated with numerous examples. One example shown here in the bottom left figure shows the ecological similarity as measured by a particular metric, here the Bray-Curtis similarity coefficient, and how it decreases with geographic distance, so spatial distance, in the similarity of planktonic communities. But this is a general principle that applies to almost any ecological attribute, and certainly any biological community, where the similarity decreases as one moves farther and farther apart in both space and time. This idea is often represented and described as an ecological neighborhood, the idea that any ecological entity, for example, an individual organism, has a neighborhood around it in space and time, where the relationship it has to neighboring entities decreases in strength as one increases the distance in both space and time. So consider a tree in the center of the ecological neighborhood in the figure in the upper right, and think about the area around that tree where it has an influence on, let's say, things like shading, light, and moisture levels, where close to that tree, that tree has a strong influence on light, energy, and moisture. But as one moves farther and farther away from that tree, its influence decreases. And at some point, it becomes essentially zero, where it has no effect on the surrounding neighborhood. And conversely, we can think about this ecological neighborhood in reverse. It's the relationship between things around the focal entity and how they influence that individual. So think again about our example of the tree in the center of this neighborhood, and think about neighboring trees and the trees in its neighborhood that exert some influence on that tree through, say, light, shade, temperature, moisture, competition. And again, trees that are closer to that focal tree are going to have a stronger impact on the microclimate and the resources available to that focal tree. This general principle, again, holds to virtually all ecological attributes and is one of the fundamental laws of ecology. Think about this example where we take an aerial image of a landscape, in this case in the high Sierras of Northern California, and consider a transect across this landscape as we move from west to east. And think about the ecological similarity between locations as one moves farther and farther apart along this transect. And invariably, as one moves farther and farther away, the ecological similarity will decrease. And again, this holds true regardless of the ecological attribute. What varies is the form of this ecological decay function. In some cases, the ecological similarity will decrease rapidly as one moves farther and farther away. In other cases, the similarity might remain quite high for some distance or some time, and then decay rapidly. But again, what holds true across all attributes is that there will be some sort of decay function with increasing distance in space and time. The second important point is that landscapes exist as spatial patterns that emerge at a particular scale as something more than the sum of the components. We call this a gestalt. And this gestalt emerges to affect a particular process. So if we think about the figure on the lower left, where we are zoomed in to an aggregation of trees, the trees themselves don't have a pattern, but the trees in aggregate or collectively exhibit a pattern. The pattern, if you will, emerges from the collective properties of all the individual trees or entities that comprise this pattern. That gestalt, that pattern that emerges, is something that can't be described by the individual trees. It can only be described by looking at the trees in aggregate or collectively. And that pattern emerges based on the spatial properties of all of those trees in aggregate. And as one shifts from one scale to another, we have what's called a gestalt shift. That is, the patterns that emerge at one scale can differ quite dramatically from the patterns that emerge at another scale. And we call this a gestalt shift. The third major point is that, and this derives from the previous 2 points, is that landscapes exist at multiple scales, depending upon the pattern and process under consideration. And there may be different processes operating at each scale. So for example, if we are interested in vegetation patterns on the landscape at fairly broad scales, we might be linking those vegetation patterns to the process of habitat fragmentation, while those same vegetation patterns at an intermediate scale might be linked to the process of fire behavior. And again, those same vegetation patterns at a fine scale might be linked to the process of bark beetle invasion. So the same patterns might be linked to different processes at each scale, giving rise to a different landscape pattern process at each scale. Conversely, we may have the same process, in this case, fire behavior, exhibit or be realized differently at each of several scales. So for example, at relatively coarse scales, the fire behavior may interact with the vegetation and the physical landscape to create what is called a fire regime. Whereas at moderate scales, fire behavior may interact with the vegetation and the physical landscape to create fire severity patterns within individual fire events. And at finer scales, fire behavior may interact with the vegetation and the physical landscape to affect tree mortality. Again, same process here, fire behavior, but realized as 3 very different pattern process relationships, depending upon the scale. So these 3 points have important implications. The first being that landscapes can be defined at any scale, so long as there is a relevant pattern process. The important distinction here is that at each scale, there is a relevant pattern that emerges to affect a process that is of interest. And it's the emergence of this pattern process that creates the landscape. And because these patterns can emerge through a gestalt shift to affect different processes at each scale, we therefore have landscapes potentially being definable at a wide range of scales, each scale being pertinent to a different pattern process relationship. Secondly, measured landscape pattern process is scale dependent, which derives from the previous points. That is, when we measure pattern and relate it to process, that measured pattern process relationship is specific to the scale at which we measure the pattern and process. In this example, from the Oregon Coast Range, we're looking at the trajectory of change in the percent of the landscape in an old growth forest condition over time. And what we see is at the coarsest scale, the province scale, we see a rather dampened range of variability in what percent of the province is in an old growth condition at any point in time. As we move to a finer scale nested within the province, in this case, the Siuslaw National Forest, we see the variability increases over time. And when we move to the finer scale, the late successional old growth reserve scale, we see the variability is quite dramatic. If we were to describe the natural range of variability in what percent of the landscape is in an old growth condition over time, clearly here you can see that it totally depends upon the scale of the landscape. At the coarsest scale, the range of variability would be relatively narrow, and at the finest scales, the range of variability would be rather extreme. Therefore, we cannot extrapolate landscape pattern process across scales. What we realize, what we observe and measure, for example, at the local scale or the site level in this example, is going to be very different than what we measure and realize at a coarser scale, in this case, the geophysical unit scale. And that, of course, would vary with the next scale, in this case, the subbasin scale. At each of these scales, what we measure or observed in the pattern process relationship will vary quantitatively and qualitatively. Hence, a landscape pattern process often requires a multi-scale approach. Because patterns and processes emerge at different scales, and more than one scale and one pattern process may be of interest in any particular application, oftentimes it requires that we adopt a multi-scale approach to defining and measuring and studying and managing landscapes. The important take-home message for this presentation is that landscape patterns and processes vary with spatial and temporal scale. Thus, the choice of scale is paramount. And whatever you do, make scale explicit and convey that scale in all of your findings and communications. This leads to axiom number 2 in landscape ecology, and that is that landscape pattern and process is scale dependent. This is Dr. Kevin McGarrigle signing off from this episode of Land Eco Lightning Talks. I hope this talk has been helpful and hope you join me for my next lightning talk. In the meantime, keep on thinking like a landscape.